Okay, hello, ladies and gentlemen. I'm Huan Wei from the Hong Kong University of Science and Technology, CSE department. I'm little tense. This is my first time in LOK, and I'm glad to be here to give a presentation. Our work is to predicting student performance in interactive online question pools using mouse interaction features. First, I want to thank company TrumpTech and the Hong Kong Innovation and Technology Fund to supporting this project. And of course, thank our collaborators from MIT and the HKU. Nowadays, especially now, online questions are very popular, and with the development of media technology, and there are a lot of interactions or different interaction types on the questions for the K-12 students. I select three questions from three different platforms. They contain a lot of interactions here, and so for the mouse interactions in online questions, for example, in this question we have the students are required to make a new shape which has an area of 6th grade. Then the students move the red dots to this or this or this part. From the data from the interaction data heat map, we can understand the students focusing part in this question, and we can understand the solving procedure, or if we do some further visualizations on this data, we may understand the student problem solving habits. So the interaction data can help with us to do some prediction, and the student performance prediction can help with the course designers to better handle the possible dropout and to improve the retention rate of online learning platforms, or to provide students with personalized instructions. And for the prediction, problem solving feature extraction always done by most of the researches. From the previous research, we have extracted, or we have summarized the three major types of features, like the basic feature of some students' personal information like gender, race, and historical records features like score statistics, or the interaction features like response time, which is the time that the students in the question and give some reaction, or the reading rate, and of course click stream. But however, they didn't consider the mouse movement features. This is because the mouse movement features are very complex. The mouse movements data usually a time sequence with many possible noises, and it's hard to extract or to define semantic or meaningful features from the sequence. So as for our work, we summarize the task and propose our prediction framework. It contains three modules: data collection and preprocessing, and we collect the historical records from the student submission, and we collect the mouse movement trajectories of the students. And for the second part is the feature extraction part. We extract statistical features from historical records, like this, and mouse movement features from the trajectories. We also make use of two feature sets to generate a question similarity matrix, which is required in prediction part. So for the prediction part, we make a forecast prediction and the evaluation. We just choose some traditional machine learning models like GBDT or RF or something. And for the evaluation, we select the accuracy weighted F1. And for our data set, we have collected about 858,000 historical records from September 2017 to June 2019. And for trajectories, we collect the trajectories from April 2019 to June 2019 on two question sets. They are area dimension question set and the deductive geometry question set. For the scores, usually the student scores on questions ranges from 0 to 100. However, it is almost impossible for us to predict the exact score for a student on a question. So we then make a 4-class prediction. We divide the score into 4 classes, like 0 represents the score range from 0 to 25. And these are 2 examples for of the 2 question set. The left one is area dimension, and the right one is deductive geometry dimension. And you can see that the right one is much more some kind of complex than the left one, because it requires students to know the knowledge of angle. And for our feature extraction, we extract 3 feature sets. They are change point features, and mouse movement features, and historical statistical features. Each of them consists of several parts of features. As for the think time, think time is a time period that students need that the teachers give some time to the students to think about the question and give some and receive some answers. However, in online circumstances, there is no teacher, and we are not sure how long it takes for students to think. Parallel studies on quantifying students' think time in traditional classroom learning cannot be directly applied to interactive online question pools. But now we have some interaction data of the students with the questions, and we can make use of interaction data to detect the think time. And to detect the think time, we will make use of the change point detection method. Change points are time points that abrupt change happens during the problem-solving process. Sliding window is a common method for abrupt change detection in the time series data. So we make use of the sliding window to help to detect the change point. In sliding window, there are 2 key parameters, a window size and detection threshold. I will illustrate the algorithm in this example. For example, in this example, we set the window size of 5 and the detection threshold to 0.7. And in the first window, we have two red dots, which is a drag event, and 3 green dots, which is a mouse move event. And then we get a mouse drag event density at 2 over 5, which is 0.4. And then we slide this window until the mouse drag event density is higher than the threshold. Then we take the first point of the window as the first change point, and then we slide the window until the density threshold is until the mouse drag density is lower than the detection threshold. Then we take the last point of the window as the second change point. So change points implies different solving stages during the problem solving process. Then we take the first drag and drop in think time, which is the time before the first change point, and first attempt, which is the time between the first change point and second change point. So for the second feature set of the mouse movement feature set, for the mouse trajectories, we defined several features to represent its statistical measurements, like the drag and drop trajectory length. So the red dot is from B, we drag the dot from B to C, and this is our drag. So the drag, we take the drag, the trajectory length, and of course the trajectory duration, and we also extract the direct length of B from B to C, which is the child length, and of course we extract the curvature, which is the delta over D, and T idle drag and drop intervals, because the green is a mouse movement, and the red is mouse drag, and the green is mouse move, and this is mouse drag. So they are intervals, and of course the mouse event intervals. And we apply the median and IQR and mean method to extract the values of the 6 features. So for the historical statistics, there are 3 types of historical statistics we extracted from the records, like question statistics, like difficulty and dimension, and student statistics, like average score, and student recent statistics, which may implies or helps us to infer the students' performance in the recent days. And if we want to make use of mouse trajectory, here is the typical framework in prediction. In past works, we make use of the static data like question feature or historical records to train and apply the new data into the model and make a prediction. However, now we want to make use of mouse trajectory. But how to predict performance with mouse trajectories? For a student, mouse trajectory is unavailable before a question is finished. As you can imagine that if I didn't finish this question, the mouse trajectory is not available. So we take a mouse trajectory from the most similar question which a student has finished, and then extract features from the mouse trajectory of that question, not the candidate question. And finally, the student performance prediction can be done. So to get the most similar question, we make use of the heterogeneous information network. The information network is called heterogeneous information network if the type of objects larger than one or the types of relations larger than one. Otherwise, it is homogeneous information network. Also, in figure A, it is a heterogeneous information network. So we have 3 types of nodes and 3 types of relations. So this is called a heterogeneous information network. So another important concept is a metapath. A metapath is a path consisting of sequence of relations defined between different objects. So for this network, we have a metapath like this, figure B, author, paper, venue, paper, author. So even if you remove this author, it can also be called a metapath. So for metapath, we have a metapath-based similarity framework for between any 2 objects in the network. As you can see this is a calculation formula, where P is some measure defined on the path instance P between X and Y. So in our work, we have a much more simpler network. We only have 2 types of nodes, which is question and students. And we make use of interactions of all students who have finished the 2 questions to calculate similarity. So the similarity score between questions can be calculated by this formula. And then now we can get a question similarity matrix. If we can get a question similarity matrix, we can find a similar question for the candidate question the student want to solve. And then we make use of the features from the similar questions. So we can fill this part. We find the similar questions trajectory and extract the features and combine with the historical features or the question features and apply them to the model. And then we can make predictions. So in our method, we applied machine learning models with newly proposed features and statistical features. As for the baseline, we applied machine learning models with only statistical features. And for the machine learning models, we choose graded boosted decision tree, random forest, SVM, and logistic regression. And as for our evaluation metrics, we choose accuracy and weighted F1 and area under a curve. So we applied different evaluation method to evaluate our results. So for our results, because we are doing a 4-class prediction among the 4 machine learning models, our method could for the overall results, our method could outperform baseline or achieve similar results. As you can see in the left figure, the green bar is ours and the gray bar is the baseline. And especially in the GBDT, our our method can achieve a accuracy score of 0.75, but the baseline is only about 0.55. For the left chart, you can see that our method could achieve 0.83. However, the baseline is only 0.6. But overall, the green bar or our method is most of the time is higher or equal to the baseline. So because we are doing a forecast prediction, we need to check the prediction on each score class. So as you can see, this is the real category or real class of the students on the score on this question, and this is a predicted score, and this is our method, and this is the baseline. So the red box represents the true positive proportion of each score class. For example, in this 0, 0, the real score is 0, and our prediction is 0 too. And we got a 0.629 accuracy. However, in the baseline, they only get a 0.514. So for the other three, it's almost the same. Ours is performance always better than the baseline. So for other three algorithms, as you can see, ours most of the time ours is performs better than the baseline in each class. So for the conclusion, we propose the novel features like sync time based on the student mouse movement trajectories for student performance prediction. And so we also propose the novel approach to incorporate historical problem-solving information on similar questions into performance prediction on new question. Finally, which is most important, that we make extensive evaluation with real-world dataset. Thank you. This is all. I'm glad to take any questions.